Okay, here's a couple of practice questions. This first one from the AQA legacy specification, the old specification, still very relevant though, on Module 5, paper 2015, if you want to look it up. Right, so we've got, it's about the hydrogen fuel cell, and that is quite a confusing topic, so I would make sure that you know it well. Right, so here's the hydrogen oxygen fuel cell that operates under alkaline conditions, it says, and that makes it a bit tricky when you're writing the half equations. Right, the hydrogen, right, that's on the left side of the salt bridge, so that of the diagram, so that must be the negative electrode, and the oxygen is on the right hand side, so that must be the positive, and that might be helpful later on. Right, I would do it this way. So it says write half equations for the reaction that occurs at each electrode. Right, let's start off with the negative one. We've got H2 gas going to H2O. Right, now the hydrogen, let's look at the oxidation numbers. The hydrogen is oxidation number 0 there and +1 there. So that means the hydrogen has been oxidized, each hydrogen by 1 electron. So there's 2 atoms, so that means we need to put 2E minus here on that side. Right, the next step is to balance for the charges by adding OH minus ions. We have two negatives on the left, on the right, sorry, and none on the left. So that means we need +2 OH minus there. Finally, we need to balance for the waters. So we need to make that balance. We need 2 waters there. Okay, so that is the negative electrode. Let's remember that. That's the half equation negative. The positive electrode, right, this is the oxygen. You start off with O2, and it ends up going to, you can see there, it goes to OH minus, the reduced form. Now, let's do oxidation numbers again. So oxidation number of oxygen here is 0, and here it is -2. So each oxygen has been reduced by 2 electrons. And there's 2 oxygen atoms, so that means we need 4E minus on the left side of the equation. Then we balance charges. We've got 4 negatives on the left and only 1 negative, only 1 OH here, so we need to multiply that by 4 OH minus. Then finally we balance by adding water. Well, we need to make it balance, we need to have 2 water molecules on the left-hand side of the equation, 2 H2O there. Right, now it asks us to use these half equations to deduce an overall equation. So we're going to have to multiply this one by 2, because there's only 2 electrons there, and we've got 4 electrons for the oxygen side. So let's do that. So we get 2H2 plus 4 OH minus, and then from the positive side we want O2, 2H2O. Then from the negative one, we get 2H2O made, and we get 4 OH minus made from the positive one. Right, let's cancel out anything that appears on both sides of the equation. Well, we can get rid of the OH minus there. Oh, I forgot to multiply that by 2. That should be a 4. 4 waters there, sorry. 4 H2O. So I can get rid of 4 OH minuses. 4 OH minuses there. I can get rid of these 2 waters, and that means we've got to turn that 4 into a 2. So overall, the equation is the very familiar 2H2 plus O2 goes to 2H2O. So we're just oxidizing the hydrogen to form water. Right, 5A then. State and explain the effect, if any, of increasing the pressure of oxygen on the EMF of the cell. Right, now, if we increase the pressure, we've got to think about this half equation here. Where are we? Let's go yellow. This half equation. If we increase the pressure of oxygen, that's like increasing the concentration. Le Chatelier says the equilibrium will try and use up the oxygen, it will move to the right. That means it's better at accepting electrons. Does that mean it's more positive or more negative? It means it's more positive. Right, so from that, we can see that the EMF with the cell, E cell, would increase, because E cell, don't forget, is going to be E right, which is the oxygen, minus E left, which is the hydrogen. So if we make this one more positive, then we're going to make E cell bigger. So you would increase the EMF of the cell. Right, I've answered that question. That's written out twice. It doesn't ask you, but what would happen if you increase the pressure of the hydrogen? Let's think about that. Right, if we increase the pressure of the hydrogen, we need to look at this top equation here. There's the hydrogen. So what will it do to this equilibrium? Le Chatelier tells us if we increase the pressure of the hydrogen, it will push this reaction, the equilibrium will go that way. In other words, it will be better at giving out electrons. It gives out these electrons here. That would make it more negative. What would that do to the E cell? Well, let's have a look here. We've got the E cell equation. E cell is equal to the oxygen, the positive, minus EH, which is the negative. So if you make this more negative, that's going to make E cell bigger. You're going to get a bigger E cell by having a higher pressure of hydrogen. Okay, and then finally, this question here, the effect of increasing the surface area of each platinum electrode. Well, the platinum it's not a reactant, so if it's doing anything, it might be acting as a catalyst, so you've got a more of a catalytic surface, so you'll increase the rate at which it attains equilibrium, but you won't change the position of any equilibriums, so E cell will be unaffected. And if you increase the surface area of the platinum electrode, you would probably almost certainly reduce the internal resistance of the hydrogen fuel cell, and that would be a good thing. But it's just asking about the EMF, and the simple answer is no effect at all. Okay, so that's that question, and I've got another one here. Right, this one is from 2014. This is okay, so this is 2014. AQA Legacy again. And it's the Module 5 paper. And it's question 5 again, so you can look that up and look at the mark scheme if you want to. Right. So we've got our standard electrode potential data in this table, which is usually the case, yeah? Right. Now, sorry. It says here, give the conventional representation of the cell that is used to measure the standard electrode potential of the ion as shown in table 3. So we need to look at this one here, and we've had this question before in the previous video. Well, you connect it to the standard hydrogen electrode, so let's do that. And you also have the standard hydrogen electrode is always the right hand electrode. So there's my salt bridge. The standard hydrogen electrode, you have the oxidized species next to the salt bridge, so it's H2. Phase change, sorry, H plus, aqueous solution phase change for H2 is a gas, and you will need platinum to make the connection as well. Don't forget the equation for the standard hydrogen electrode is 2H plus 2E minus goes to H2, of course. So that's our oxidized, that's our reduced. Right, now we need the ion one, which is in there. So oxidized species next to the salt bridge, that's Fe2 plus. A phase change because that's an aqueous solution of iron metal. We don't need any platinum there, and that's it there. Okay, that would be and E cell of that would be equal to the standard potential for the iron, and of course the hydrogen one is 0 minus 0, so we can just forget about that 0. Yeah, the E cell is the standard hydrogen, is the standard potential for the ion. Right, 5b, term reducing agent, terms of electrons. Reducing agents give away electrons. So they become oxidized themselves. Identify the weakest reducing agent. So the things that give away electrons are the ones on the right. These are reducers. As when the equation goes backwards, they give away electrons. And all the species on the left, they're all oxidizers, oxidizing agents. Well, it says here, what's the weakest reducing? Which is the one of the reducing agents which is the worst at giving away electrons? It's going to be one which is least negative. And the least negative side, okay, is this one here. So the worst reducing agent. Now, interesting there, is it the chlorine or is it the water that's a reducing agent? Well, the hydrogen and the oxygen don't change their oxidation numbers as you go from left to right, so they're not the reducing. It's the chlorine, because that does change its oxidation number. It goes from Cl2, which is 0, to this stuff HOCl, where its oxidation number is +1. So you can see the chlorine actually gets oxidized. Now, chlorine is a very poor reducing agent. See there. Okay, so that's how we do that. Right, just get rid of all this. I didn't mean to do that. Good, it's let me got it back again. Right, let's rub that out. Right, it says here, when HOCl acts as an oxidizing agent, one of the atoms in the molecule is reduced. Which one is it? Well, I've kind of answered that already just before what I said. It's the chlorine, because the chlorine has got an oxidation number of +1 in HOCl, whereas in Cl2 it's got an oxidation number of 0 on combined elements. Okay, then it says, explain your answer in terms of the change in oxidation state. So I've just done that with the oxidation numbers. Use the information given in table 3 to deduce an equation for the redox reaction that would occur when hydroxide ions are added to HOCl. So we need to look at our table there. Right, we've got HOCl here. And the hydroxide ions, well, we've got hydroxide ions up here with the zinc, but it doesn't ask us about the zinc, so we're not talking about that. We're talking about these hydroxide ions. Right. Now, that's good. There's a possibility of reaction here because these are the oxidizing agents and these are the reducing agents. So HOCl is an oxidizing agent, perhaps OH minus can act as a reducing agent. Let's have a look at these two half equations. We need to look at these two. Which one is the most positive? Is this one. So that's the best at taking in electrons. So that one is going to go forwards. And this is the most negative, this one. So this one is best at giving away electrons. So that's going to go backwards. So that gives us the direction of the reaction. So we just need to do, but we need to bear in mind, we need to multiply this one by 2 because this is a 2 electron process and that one is 4. So let's do that. So we're going to get 4 OH minus plus 2 HOCl, hypochlorous acid. Sorry, 4 HOCl because we've got to times it by 2. Plus 4H plus uh, 4H plus is going to turn it into O2 2H2O, chlorine, 2 chlorines, and another 4 H2Os. Now we're going to do a bit of cancelling out of things there, I think. Right, so what we get, well, 4OH minus and 4H plus, that makes 4H2O, plus 4HOCl is going to go to O2, and we add these two together, gives us 6 waters and 2 Cl2s. Right, but that means we can get rid of those waters on the left and change that into a 2. So the answer is 4HOCl goes to O2 plus 2H2O plus 2Cl2. And that is a bit funny because the OH minus is not actually, doesn't appear in the equation, okay? But it says what happens when you add hydroxide ions to the HOCl. Well, it obviously pushed the equilibrium in this direction, but the OH minuses don't actually appear in the equation. Okay. Right, this question carries on. It's quite a long question over here. And this time they're talking about a, we need to use this table, but we need to look at this bit first. This is a hearing aid battery. It's an electrochemical cell used to generate a voltage, okay? And we see here, what's it got? It's got an air hole. I think that's going to be to allow O2 coming in. That's what a reactant. And we've got, this is alkaline, aqueous alkaline paste here. And in this bit, we've got zinc powder. Okay, and that's also an alkaline solution, or alkaline paste. Right, now use the data from table 3 to calculate the EMF of the cell. So the difficult thing is we've got to decide, well, what's going on here? Well, we've obviously got zinc here, so let's have a look at this equation. This half equation is going to be needed. Yeah, we have, look, we've got zinc and the OH minus, that's in the alkaline paste, yeah, there. And that's going to form to make zinc oxide, probably. And then what's the other equation? Well, there's no iron in there, so it's not this one, definitely not that. There's no HCl, it's not that one. So it's got to be this one here. And we've got oxygen, which is being reduced to the hydroxide ion. And yeah, we've got oxygen here coming into the air hole. So it's those two half equations. That's quite tricky, really. You have to think, you know, air, it's the oxygen in the air that's going to react. Right, so we need to think about these two equations, which way they're going to go. Which is the most positive? The most positive is the oxygen one here. So that one is going to be best at taking in electrons. So that one's going to go forwards, which is the most negative, is this one. And that's going to be best at giving away electrons. So that's going to go backwards. Okay. Now, do we need to do any multiplying? Yeah, we do, because that's 4 electrons and that was only 2. So we've got to times this one by 2. So let's write down 2 ZNO plus 2 H2O. Sorry, that's the wrong way. We're going to have 2 Zn and 4 OH minus. And that's going to react with the oxygen and the water. So that's going to be plus O2 plus 2 H2O. And that is going to go to two zinc oxides, 2 H2Os. And then from this equation, we're just going to have 4 OH minus. Is there anything we can get rid of that appears on both sides of the equation? It's the hydroxide ions. So we'll get rid of them and them. and then we can get rid of the waters, can't we? So we're going to get rid of those waters and those waters. So all that's happening is that the zinc is reacting with the oxygen to form zinc oxide. That is the cell reaction there. Right, this one, question 5. Which A or B is the positive electrode? Okay. Right. Now A is here. So A is the O2 electrode, and B is the zinc electrode. We have to decide which one's going to be positive. Well, look, the oxygen is a lot more positive than the zinc. That's plus 0.4 volts. That's minus 1.25. So this is the positive. A is the positive and B is the negative. Right, now this last question, 5F, suggests one reason other than cost why this type of cell is not recharged. And it's not a very satisfactory answer. If you look in the mark scheme, it just says this reaction cannot be made to go backwards, which to me is not a brilliant answer, but that's what, it's only one mark and that's all they wanted apparently. Incidentally, you may think, why are some batteries rechargeable and some other ones aren't? Some not this battery here, but some batteries will do things when some cells, the cell reaction will lead to the production of things like hydrogen, and that hydrogen is then just going to diffuse away into the air. So it's not going to be, you can't reverse the current and make that hydrogen react backwards because it's gone, it's disappeared. So that's one kind of obvious reason why some cells are not rechargeable. But this one, as I say, the mark scheme just says because you can't reverse the reaction. It doesn't really explain why. Okay.